So here in example 5, we're trying to figure out how fast the depth of the water in the cone on the right is decreasing when the water level is 6 feet, given that the water is flowing out at a rate of 1 cubic foot per minute. Okay, so what do we know and what are we looking for? We know that we're trying to find how fast the depth of the water is decreasing. So what represents the depth of the water? Let's give this some variables. I know this is R and this is H for a cone. So the depth of the water based on those variables would be dH dt. They're trying to figure that out when the water level is 6 feet high. So that means when H equals 6 feet. And they told us that the water is flowing out at a rate of 1 cubic foot per minute. So that's dV dt equals negative 1 cubic foot per minute. So now that I know what I know and I know what I'm looking for, what equation can I set up that connects these variables? Well, I know I'm given dV dt, so I should be doing something with volume. From geometry, I know that the volume of a cone is 1/3 pi r squared h. So I can differentiate this now with respect to time. dV dt equals pi over 3. And right here, this is product rule. So the derivative of r squared is 2r dr dt multiplied by h multiplied by r squared dH dt. So now I can plug in what I know and see what and solve for what I'm looking for. Well, I know dV dt and I'm looking for dH dt. I know h, but I don't know what r is and I don't know what dr dt is. So this is getting a little confusing. I know my overall goal is to find dH dt, but I'm stuck right here because I don't know these variables. So what if I revisited the problem from the very beginning and I tried to figure out how I could write this equation only in terms of one variable, h? Well, let's look at the relationship in our cone to begin with. I see that the common ratio between my radius and my height of the overall cone, I know that my ratio of my radius to my height is 4 to 12. So if I solve for r, r is 1/3 h. And that is true. Anywhere we are, it'll be proportional. So now I can start back with V equals 1/3 pi. Now instead of R, I'm going to plug in 1/3 h squared multiplied by h. Now instead of having two variables, I've used my relationship here, the ratio of my radius to my height, to change my equation to only one variable. So let's see, 1/3 squared is 1/9. So V equals pi over 27 times h cubed. This is a much easier equation to differentiate now, and I'll only have to worry about V and h. So let's figure out what this is with respect to time. dV dt equals pi over 27 multiplied by 3h squared dH dt. So perfect. Now I can plug in what I know and solve for dH dt. So I'm not going to isolate it first in this one. I'm just going to plug in and find it in the end. So I know dV dt is -1 equals pi over 9, because these cancel, or I can divide both of these by 3, times h squared, well, h is 6, multiplied by dh dt, which is what we're looking for. So 36 divided by 9 is 4. So I have -1 equals 4 pi times dh dt. So now isolating dh dt, dh dt equals -1 over 4 pi, and the units for this would be feet per minute when h equals 6 feet. So the rate of change of my height is -1 over 4 pi feet per minute when h is 6 feet. So we see it's negative, which is what we're looking for. The height should be decreasing if the water is coming out. So let's go ahead and leave number 6 as a warm-up. We'll try this in class together, as well as number 7 will be a warm-up, and number 8 will be a warm-up. So we'll do those in class together, along with some visual demos.